all that? Okay. So we're going to continue with gases today, and it's kind of at some point near the end of part 3, when you hit the assignment slide, I'm going to assign the first 2, and then I'm going to go into something else. That's the extension, and then we probably won't get to the last 2 problems in your assignment slide. But you may or may not in high school you were exposed to PV equals nRT. I know it, the ideal gas law equation, but I don't know how much you dabbled with partial pressures, and that's kind of what we need to talk about. And this kind of makes me smile because oftentimes gases, you don't have a pure gas. Like, for instance, in this room, we have like 80-20, like nitrogen, oxygen running around in this room. So the nitrogen exerts a pressure, a partial pressure of nitrogen gas, and the oxygen gas particles also exert their own kind of partial pressure. That's what we call the partial pressure of nitrogen, partial pressure of oxygen. That's kind of what we're talking about, gas mixtures. So for instance, in this case, we have hydrogen shown in there, and of course, little weights are kind of on the free-moving piston thing, so the weights are an indication of the pressure of the gas particles being contained in that glass jar. Got the volume is 5 liters, the temperature is 20 degrees Celsius. N of H2 is 0.50. Okay, bless you. So we could do the whole PV equals nRT, and we would reconcile that these are the right pressure, volume, and temperature, number of moles for hydrogen. Okay. Now another gas, helium. So notice that actually the pressure of the helium gas confined to the same volume is greater. Okay, so we have 6 atmospheres of helium, 2.4 atmospheres of hydrogen. What say we take those 2 gases, the blue and the red one, and have them combined in the same container, 5 liters. Okay, looks like a pretty sort of deal, doesn't it? Same volume, same temperature. Now notice we have our 0.5 moles of H2, 1.25 moles of HE. But notice now the pressures are additive. Dalton's law of partial pressures says that if you have independent gases exerting a pressure, if you combine them to the same volume, the same temperature, you just add the pressures. So now notice 2.4 plus 6 is equal to 8.4 atmospheres. That's exactly what you have over there. Okay, it's kind of a neat thing. But remember that gases are like, they're your wild children, that basically you're going to have definitely a homogeneous mixture over there. Okay, so not so surprising. So this kind of talks you through a similar thing that we just looked at. In this case, each of these flasks, aren't they cool? They're kind of like your burettes with the stopcock down here and a stopcock up there. So we're going to put 3 gases in here, gas A, gas B, and gas C. Okay. The number of moles of gas particle A is N sub A, you get it, etc. Number of moles of gas C is N sub C. Okay. Those containers, these glass flasks, are all the same volume. They're all at the same temperature. So the blue V and the red T, constant. Well, these at the top there actually have little pressure gauges. They're kind of like a little dial thing where the higher the pressure, the more it dings over to the right. Okay. So we could say that the partial pressure, or the pressure of A, okay, I guess it's not combined with anything else, so just the pressure of A is equal to the number of moles in this container times the ideal gas law constant times this common temperature divided by this common volume. We could do the same thing for the other 2 gases. So we have 3 different gases. It's almost like a magic trick. Well, over here we have a container waiting, and we're going to take the contents of each of those 3 containers, those 3 gases, we're going to combine them into this one container. Guess what? This one container has the same volume as they came from, and it's at the same temperature as what they came from. Common volume, common temperature. We could actually say that the total number of moles of gas particles over here when we combine A, B, and C is equals to the moles of A plus the moles of B plus the moles of C. Okay? And we could say that actually now they're all crammed in there together. It's going to be greater pressure than any of them individually, isn't it? They're all crammed in there together. They're creating a combined pressure we call the total pressure. That's what a little subscript T is, total pressure. Sometimes I do a capital T instead of a lowercase t. So according to the PV equals nRT, okay? And I'm going to try to kind of convince you why this is, I think. But if we combine those three gases, okay, we can come up with the total pressure, not the individual, but the total pressure by taking the total moles times R times T divided by V. It's a wonderful thing. And this kind of goes back to, we kind of don't care what the gas particles are as long as they are behaving ideally. On Wednesday, we're going to talk about more about gases behaving not ideally, when gases go wrong. So I'm going to kind of show you a little bit of a proof to take that, the total pressure is equal to the total number of moles times R times T divided by V, kind of back it off into the individual pressures. I'll show you how this works. So we could expand the total number of moles into the sum of A, B, and C. And then we know that actually we can take that sum and we can multiply it by RT over V. Okay? And we have basically then kind of distributed it, and it looks like this. The total pressure that we saw over here, kind of in the first chamber from your left, okay, is equal to the number of moles of gas A, RT divided by V. Number of moles of gas B, okay. Well, these terms, we know what these are. These are the individual partial pressures of the individual gases. Okay. This right down here at the bottom with the blue box, you know, it's funny, there's things in science you're like, well, no, duh, right? This might be one of them, okay? The total pressure exerted by the combination of all three gases is equal to their individual pressures together, okay? Makes sense. It's kind of a cool thing. I'll buy that. And that's Dalton's law of partial pressures. Earlier in this class, we talked about the atomic theory, or Dalton's atomic theory, the same dude. Guess he was colorblind and a school teacher, and so I buy that. Okay. Well, there's one more kind of important thing we're going to kind of massage out of what we've just been talking about. Okay, so let's pick on component A, gas A. Partial pressure of A is equal to the number of moles of that gas times R times T divided by V. Okay? When we take A and combine it with B and C, the total pressure is equal to the total number of moles, RT divided by V. Okay, exactly. Now, especially in Chem 2, we do a lot of this. We're basically going to take the top equality and we're going to divide it by the bottom equality. And it looks like this. I know it seems kind of strange. There's the top one. We're going to divide by the bottom one. You're like, why would you do that? Well, if we do that, notice that the R's, of course, cancel. The R term cancels. The temperatures are the same when it's an individual component or when it's a mixture. They are in the same common volume. Okay? So basically, that all boils down to the partial pressure of A, that one component, gas, what its pressure is, divided by the total pressure is equal to the moles of A divided by the total number of moles. And this is a cool thing. Usually it's seen this way. If, and there are definitely problems, chemistry problems, that this is the case. If you know your total pressure, and you know the relative moles of your component of interest, component A, to the total number of moles of gas particles, okay, you can take this ratio, which actually we're going to call that, we'll call it the mole fraction. This is the mole fraction right here. Does it look like a mole fraction? The total number of moles of A to, the number of moles of A to the total number of moles. It's a mole fraction. Times the total pressure to get the partial pressure. It's a wonderful thing. The variable for the partial pressure of a gas is X with a subscript, whatever the component is. So the mole fraction of A is X sub A. So now that equation becomes this, where the partial pressure of any component is equal to the mole fraction of that component times the total pressure. And that can be a helpful thing. And it makes sense. The mole fraction should always be less than 1. The X of A is always less than 1. So you're always going to have your pressure of A is always going to be less than your total pressure. And it makes sense. It can be quite handy. All right. Well, let's do a couple problems. Okay, so in this case, we have a gas mixture of carbon dioxide, nitrogen, and neon. Let's see, do I have the question here? Oops. I guess the question is there. We got time. Here's my thing. Okay, we can make blue the CO2. So it's all 2 grams. And we can make purple the nitrogen. And we can make red the neon gas. All running around in there. Very colorful. Okay, determine the partial pressure of each gas in the vessel and the total pressure exerted by the gas. Well, let's go over here on the side, kind of like we had been doing, and let's write pressure, volume, number of moles, and temperature. It does get a little interesting, though, in this case. Let's hold off on the P in the end, but the volume, 5 liters. We got that. Temperature, 15 degrees Celsius. And we're going to have to convert that to Kelvin. Determine the partial pressure of each gas. Well, can we come up with let me go ahead and, there's different ways to work this, but let me put a little subscript T next to my moles. Can we come up with a total number of moles of gas there from there? Yep. There's different ways to work that, but that would make sense to me. I would probably do it that way. I'm going to get total number of gas, moles of gas over there. And then I'm going to say from masses. And then we're back to, we can use PV equals nRT to get P sub T. Okay, so then P sub T, the total pressure, I'll just put it this way, PV is equal to NT RT. Okay, so then we'd have everything but that. That will give us the total pressure. So this is a good example. I wanted to mention this. Do you see where it says it wants the partial pressures and the total pressure? To me, what makes most sense is to get this one first. That's what I would do. You'd be like, well, it doesn't say it first. Well, who cares? I'd get the total pressure. Okay. And then second, okay, I actually then would use, I'll just use example of CO2. I can get the partial pressure of CO2 by taking the mole fraction of CO2 times the total pressure. And that's exactly what I'm going to do. I'm going to do that for the other two. So kind of in a nutshell, that's what I would do. And that's what my slides do. So we need to get the total number of moles from those masses. So here we go. You would need to, on a test, come up with the molar mass of CO2 again. The molar mass of CO2 is 44.01 grams per mole. So we take 2.00 grams times 1 mole over 44.01 grams. Grams cancel. 3 significant figures, because that's what we have in the mass. 0.0454 moles of CO2. Then we need the moles of N2. Again, we have a mass of 2.00 grams of N2 times 1 mole over 28.02 grams. That's the molar mass of N2. And grams will cancel. We're left with moles. So moles of N2 are 0.0714 moles of N2. And last but not least, we had the same mass of neon, the 2.00 grams of neon. The molar mass of neon is 20.18 grams. So then we take 1 mole over 20.18 grams. Grams will cancel. We're left with moles of neon. Whew. And actually, we're going to use these moles to do our partial pressures here in a minute too, so this works out well. So of course we add them all together. Since we're adding, we round according to decimals, but it looks like we have 4 decimals and everything, so we're allowed 4 decimals. So if you line them all up and add them together, your N sub T, your total number of moles, is 0.2159, because we have 4 decimals, remember. So that's our N sub T. These always seem so long, oh my gosh, because now we need to use the ideal gas law equation. Yep, here we go. So we rearrange P equals nRT to solve for P. So the total pressure is equal to the total number of moles times R times T divided by B. So here we go. We needed to fix our temperature. It was given in Celsius, so 15 degrees Celsius plus 273 units is 288 Kelvin. So we should be fine then. Now we're ready to plug in. So the total pressure is equal to the total number of moles, 0.2159 moles, times the ideal gas law constant, 0.082058. Units of R are liters, atmospheres per mole Kelvin, the R we're using, times the temperature in the Kelvin scale is 288 Kelvin, divided by the volume that was containing these 3 gases, which is 5.00 liters. My favorite part of working chemistry problems is canceling. I don't know about you. So moles, cancel. Liters, cancel. Oh, duh. And Kelvin cancel. So we're left with units of atmospheres. Rounding to 3 significant figures, because that's what we have in our temperature and our volume. The total pressure is 1.02 atmospheres. So that was the second question. Now we're going to use that total pressure to get the partial pressures. So it looks like this. So to get the partial pressure of the CO2, we take the moles of CO2. If you flip back a few slides, you have 0.0454 moles of CO2 divided by the total moles, which is 0.2159. That's your mole fraction. That's your X sub CO2 times the total pressure, 1.02 atmospheres. Looks like we need to round according to 3 significant figures. So we got 0.214 atmospheres is the pressure exerted by the CO2. That does 2 grams of CO2 in that container at that temperature. So the partial pressure of N2 is the moles of N2, 0.0714 moles, divided by the total number of moles, 0.2159 times the total pressure, 1.02 atmospheres again. Rounding to 3 significant figures, you get 0.337 atmospheres. Now this is where students intuitively, and they are correct, say, well, we could get the final gas by difference, couldn't we? We could take that 1.02 atmospheres and subtract the 0.214 and the 0.337, and that should give us by difference. And you're right. But just for kicks, in case we did something wrong, let's go ahead and get the partial pressure of neon the same way. The partial pressure of neon is the moles of neon, 0.0991 moles of neon, divided by total moles, 0.2159, times the total pressure, 0.102, rounded 3 significant figures, 1.02, excuse me. Rounded 3 significant figures, we got 0.468 atmospheres.
And then in the exam, though, you'll want us to do it this way and not.
Yeah.
Yeah, okay.
I think there's a good check, though. We could also just add the 3 together and see if we come up with approximately 1.02, right? Yeah. I don't think this is, but yeah. Are we good with that one? Yep. Let's do another problem. They're so fun. I think I'll write underneath kind of the species. This is a good example where you have 2 liquids going to form 3 gases, right? Now those little L's and those little G's are not any small thing. and you'll see why, or you already kind of get a sense for why. So, so here we have 150 grams of this, 3 significant figures. Oh, they're not making us find out what's in limited supply, are they? Thank goodness. Excess N2O4, okay? And these gases are all running around. I'll go ahead and draw our famous little box. These gases are all collectively running around in the same container. I'm not going to draw 3 colors, but just kind of imagine that. Okay, and it gives us some information. In fact, I think I'll go ahead and do the P, V, and T over there. Right, they give us a temperature, 27 degrees Celsius. Of course, we're going to have to convert that to Kelvin. They give us a volume ready to go of, that's a big tank, 250 through 3 sig figs liters. Okay. Notice they don't give us N and they don't give us P. But we must be able to find those. And again, we don't have to do these in order, but question number 1 says, what is the total gas pressure in the tank? So if I go ahead and put a little subscript T up here next to my P, that actually is the first question. Okay. The second question is, and we'll just go ahead and find our nitrogen. Here's our nitrogen. The second question is, what is the partial pressure of nitrogen? All right. That's where I go get a cup of coffee, okay, that sort of thing. We know that we could hammer this thing out, because you could go from moles of the dimethylhydrazine, you could go from grams of dimethylhydrazine to moles, and then you could go from moles of that to individual moles of N2, to moles of H2O, to moles of CO2. You could totally do that. But there's an easier way. I'm going to show you how you can kind of quickly go to, let me put a little subscript T. I'm going to show you how you can quickly go from moles of hydrazine to the total moles of gas. Okay? It's really not that mind-blowing. But my point here, when we work this here in a minute, is this is what we're going to get first. We're going to get total moles, and then we can, once we have N sub T, we can get some P sub T really easy. Okay. So here's how this works. Well, of course, we're going to have to convert that mass of the limited reactant into moles. So the molar mass of the dimethylhydrazine is 60.10 grams per mole. So let's go ahead and get the moles of dimethylhydrazine. It's the mass, the 150 grams, times 1 mole over 60.10 grams. That's the molar mass. Grams will cancel. We're left with moles, 3 significant figures. I always smile and like, really, it's 2.5 moles? So 2.50 moles of the limited supply reactants. So those number of moles are going to go then and produce the 3 gases, the 3 product gases. Well, I guess it's really not that bad. Can you see where the stoichiometric coefficients, if you add the 3 moles of N2, and the 4 moles of H2O, and the 2 moles of CO2, which are all 3 gases, that actually you get in total 9 moles of gases produced for the coefficient in front of the dimethylhydrazine is 1. So for every 1 mole of the limited supply reactant, you get 9 moles of gases. And this is a good example where we don't care, we don't break down which gas is doing what. We just care about N sub T. So actually that is going to be our stoichiometric coefficient. We're going to plug into our 2.5 moles of limited supply reactant. So then all we got to do is we take the 2.5 moles of, boy, that's a bear to write out. If I was doing this problem, I probably would call it DMH for dimethylhydrazine. At the top, I would just say DMH is equal to blah, 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 because I get tired of writing that out. It's fair game. Definitely can do that. So that's our first term, and then we just bring down this ratio. So 2.5 moles of DMH, dimethylhydrazine, times 9 moles of gas for 1 mole of DMH. Cool. Moles of DMH cancel, we're left with moles of so that's our N sub T, people. Is that not exciting or what? So rounded to 3 significant figures, your N sub T is 22.5 grams of gas are produced collectively, all 3 of those gases together. Which that will get us down the road to getting our total pressure, won't it? So here we go. The ideal gas law equation, PV equals nRT, solving for P, our total pressure, and we could, if I was doing this, I probably would keep my little subscripts. I would put a little, our total pressure is equal to a total number of moles times R times T divided by V. We need to fix our temperature from 27 Celsius to Kelvin, so we add 273, so that gives us a 300 Kelvin. But now when you're working this problem, don't get in too much of a hurry to recognize with 300 Kelvin, that's really 3 significant figures. Our volume was big, 250 liters. So now if we plug into PV equals nRT, our total pressure is equal to our total number of moles, 22.5 moles, times the ideal gas law constant, 0.082058. Units for that are liters, atmospheres per mole Kelvin, times the temperature in the Kelvin scale, 300 Kelvin, 3 sig figs there, divided by the volume that was containing those product gases, 250 with 3 sig figs liters. And we need to round according to 3 significant figures, so 2.22 atmospheres. There's far too many 2's in this problem. If you're like me, you know, you're just like, and then I start second guessing myself. I'm like, really? So of course you could cancel the moles and the kelvins and the liters. You'd have to units of atmospheres. So that was our first question. So now our next question is, what's the partial pressure of N2? So we have a little bit of catch up to do, not too bad. We have to come up with the moles of N2. There's a couple of different ways, I think, to work it, okay? But if we go back to, we know the total moles of product gases, we could say, oh, I guess there it is. We could say that the mole fraction is, that is pretty cool. We could say the mole fraction happens to be the coefficient in front of the N2, 3 moles for every 9 moles. So that's where that came up from. So here we go. So we're going to take that 3 moles of N2 for every 9 moles of total gases, and we're going to multiply that times the total pressure, which we got is 2.22 atmospheres. I know 3/9 is 1/3, but there you go. Rounding to 3 significant figures, you get 0.740 atmospheres. And that was the second question. And that's it. There are all sorts of variations with these problems. I wince when I think about it. Okay. So assignment slide. Okay. So what I'm going to show you is 60 and 61, and hold off 67 and 68. I probably won't be assigned until Wednesday. I know we're bumping up against the final. So probably 67, 68 will be for extra credit, 10 points extra credit. But now for those of you who have been handing in your homework on a regular basis, remember that I dropped 10% of your homework. So what I just said, actually these are going to be, we're going to cover those tomorrow, but these are going to be normal credit. And these will be due Wednesday. Yeah, I know. I hear about a bunch of other classes that aren't doing anything the rest of the week. I'm just like, really? Sigh. But 'tis not the way with this class. So, let's see. Don't know how much you really need to 60, 61. See, but okay. So this is 60. You have two gases confined, given the volume and the temperature are given. It's kind of similar to what we've been talking about. From those masses of H2 and He, you can get individual moles, and then you add them together to get total moles, right? Okay, so then you can get the total pressure using the ideal gas law equation. And then B, it says what are the partial pressures of each of the gases, and so you'll take the mole fraction of each times the total pressure. That should be pretty good. And then the next one looks like this. Oh, I know, this is really busy. It's almost like a state 1 and a state 2. So actually, it talks about taking, and they do this all the time. They take some sort of inert gas. What's more inert than a noble gas, right? So basically, you have argon over here. Okay, this is your argon is your knot player, okay? You fill your chamber with argon at a given volume and a given temperature. And the pressure of argon's given too. You can come up with the moles of argon then, right? I could. If I can, you can, okay? So come up with the moles of argon. Then the problem describes where basically this is my puddle down here. This purple thing is my puddle of benzene, okay? There's my puddle. It starts out as 0.728 grams of liquid, and it's going to all vaporize. So it's all going to be cute little purple gas particles in there amongst your argon. Okay, so of course the pressure is going to go up, right? Because now you have argon and C6H6. So you're supposed to, see, what is the total pressure? So what is the total pressure over here? Now notice they give you the mass, so assuming it all goes from a liquid to a gas, you can use, they give you the formula, so you can calculate the molar mass and use grams to get moles, can't you? Yeah. So then you just add those moles, just the argon moles, and you get total number of moles, okay? And it's the same temperature, the same volume, okay, but it's got a higher pressure. And actually that's the first thing you're supposed to do. Calculate, step 3 here is the first question. What is the total pressure in there? And then B is actually what's the partial pressure of argon of each component. And you just somehow need to look at your work and come up with the moles of each component divided by total moles times the total pressure. So that's it. Okay, so courtesy of Mr. Saluti, who, like I said, it is his birthday today. These are, I really don't think, it's not my intent to get all the way through these, to get to those last two problems. But it's good that you be exposed to this other type of gas law problem, partial pressure problem. So these don't have any words coming out very, as far as I can tell. So notice this sort of experimental setup. So the way you look at this is you think of some sort of chemical reaction occurring over here. And it is producing a gas. And that gas is being collected there. How else are you going to collect a gas, right? That's a good way to collect a gas. The problem with this, and this is kind of, well, I'll get to that here in a minute. So you have gas filling that container. The longer the reaction goes on, the greater the gas, and it's going to basically go like this. Okay, it's going to balloon up. Now, an important thing here, and it's kind of a subtle thing, but if you go ahead and take the liquid, can you see where that's liquid in the bottle? If that liquid lines up with the liquid in your beaker, okay, the liquid in the bottle, the gas over here, lines up with the liquid in your beaker, actually, then the gas that's being held in there is equal to whatever the weatherman says your atmospheric pressure is. So remember, we're walking around here, we have nitrogen, we have oxygen. That's actually what we call the atmospheric pressure. So you see P sub BAR, it's also called the barometric pressure. Atmospheric pressure, barometric pressure. So this is the pressure of the atmosphere. Barometric pressure and atmospheric pressure, same thing. So that's pretty cool. So when you work these experiments now, the thing we're going to do on Thursday, we aren't going to do this. I debated there's another one, but all you got to do is look at the weather. And when I do this experiment with basically taking zinc and having it react with HCl to form H2 gas, I look at what the weatherman says as to what the barometric pressure is. All right, cool. All right, gas collecting container to collect a gas product. Now this assumes that your gas product will not dissolve in water appreciably, because if it does, then you're screwed, right? Okay, so yeah. That would be problematic because some gases do dissolve pretty well. So like I said in that last one, if the liquid level inside your container that you're trying to isolate your gas and outside the container are equal, then your gas of interest has a pressure of whatever the weatherman says, your barometric pressure. Okay? Right. Oh, you don't want it to react with water either. Oops. Poor experimental design. Okay. Well, what does that have to do with partial pressures? Well, here's what it has to do with partial pressures. The problem is, and if I kind of go ahead and recreate what you just saw, so here's my inverted bottle, my gas of interest is at the top there. I went ahead and here's my water inside and here's my water outside. Here's my beaker. The thing about it is if you were to, oh, by the way, this gas in here, the gas of interest, the pressure of that gas is equal to the barometric pressure. Okay, that's cool. But the problem with that gas is it will be your gas of interest. Let's just say it's O2, and oxygen does dissolve in water to a certain extent. But let's just say it's O2 gas. It will also have a gas that you need to account for. And that's what I want to spend a minute talking about. Just because of the way your experimental design is, you are going to have, you can't expect not to have water vapor in there. You will have cute little water molecules running around with your gas of interest. It's just the way it is. It's life. How much? Well, actually, we have a table to tell you how much. Okay. Now, one of the things in general chemistry, too, that we're going to talk about is this whole idea of liquids going to a vapor. So that's what we're fighting here. Basically, your liquid water is going to a vapor, to a gas. Okay? And it's in what we call dynamic equilibrium. Let's see if I have a... All this says is, I'm going to, here's my inverted bottle. Oh my goodness, they're getting worse. Here we go. Let's do it like that. Here's my inverted bottle. Here's my beaker, and it's at the same level. The thing about those liquid particles is some of the liquid are going up to form, now this is my water, this isn't my O2, are going to form gas, and some of, now this is H2O, and some of your gas H2O particles are going back to form liquid. That's what we call dynamic equilibrium. Okay, it's going both ways. Yep. You're going to see a table here in a minute for water. This is my H2O. I know it's not the gas I want, but it's the gas I got because of my experimental design. Okay, there is a table to tell you what the pressure of the H2O is at a given temperature. Okay, we're assuming that basically, have you ever heard the weather person talk about 100% relative humidity or saturated air? Okay, that's what we're assuming. Basically, that little area up here has become saturated with water vapor at that particular temperature. So this is kind of trying to show you what I tried to show you a minute ago with dynamic equilibrium. The red represents evaporation. The blue represents condensation. So if you were to count, of course, this is all evaporation. Okay, this is basically you have a bell jar. Okay, that you have pulled a vacuum. It's totally dry in there. The first thing all water is going to do, if it given a chance in a dry environment, is to evaporate. Okay. Now over here, given amount of time, so kind of from left to right, we have it kind of setting time. Notice that if we were to count the red ones, which are evaporation, 1, 2, 3, 4, 5, 6. I have 6 evaporations, How many condensations do I have? 1, 2, 3. I have 3 condensations. 6. Okay, so it's still evaporating more than it's condensing. Okay, given enough time, and this is where the 100% relative humidity, this is where saturation comes into play. If you were to count the reds and the blues given enough time, they're equal. If somebody says it's at equilibrium, that's what they mean. Equal amount is evaporating and equal amount is condensing. The dynamic part, which is totally awesome, comes into play. It's not the same molecule of water that's evaporating that's condensing. It's like random, but the rates are same. The amount that evaporates equals the amount that condenses. So this chamber over here is what we call saturated. And that's what we're assuming is the case with your experiment. Okay. So over here, this last one, okay. Have you ever heard, and I tell my meteorology students this, have you ever heard that warm air, how's this go? Warm air holds more water vapor than cold air? It doesn't, the air doesn't hold it, but there is something to be said for that adage, okay? So this, that's coming up at the table. This table right here kind of emphasizes that adage. Warm air, I'll go down here to 50 degrees Celsius, warm air holds more water vapor. Now, this column over here on the right, that actually is your, if it's at saturation, what sort of pressure of water vapor pressure do you have? Well, we have 92.51 millimeters of mercury. Well, what if it's cooler? What if instead of 50, what if it's 19? What sort of pressure do we have, our water particles? 16.48 millimeters of mercury. That's the pressure at saturation, at equilibrium. Okay, so warm air does, well, it creates a greater pressure for 2 reasons. One is that there are more water vapor particles, and the other is they're moving faster. So those will kind of work together. So the point is, and we'll start out with this Wednesday. The point is, for instance, let's just say you were running an experiment at 25 degrees Celsius. If you had to account for the partial pressure of water vapor, guess what? You would say the partial pressure of water vapor is 23.76 millimeters of mercury. That's what you would say. Why? Because it's on this table. Okay? That's how that works. And this is another table. It's teeny, weeny, tiny. I know the other one, I'll just tell on myself. You know, this is page 215. I'm like, oh my gosh, is it really at 215? Yes, it is. Petrucci, this particular edition you're working. Yeah, these are way small. I know. They're teeny, weeny, tiny. I don't think you have to use these for homework, but they're terrible.
I hope not. You have to magnify them.
Okay. So like I said, the reason you're going to need to use those tables is you're going to find the temperature of the experiment, and then you're going to see what the saturation vapor pressure for water is. And that's going to be your partial pressure for water. All right. So we will pick up here on Wednesday and work that problem, then talk about non-ideal behavior, gases behaving badly. And like I said, stop by my office if you want, but I will be grading these and give them all back to you tomorrow.